Another live stream of Physics 232. This is week 7, and we are going to be talking about magnetism, magnetic forces, and magnetic fields today. I'm going to get started with posting a couple links up in the chat for anybody. So there's a few links there. One is the link to the Learning Center at Portland State University. That's the tutoring page. So that's pdx.edu/learning center/tutoring. There's a dash or hyphen between learning and center. There's also links to their Facebook and Instagram page, so definitely check those out. Follow them on Facebook and Instagram so you can get updates as new resources available. I'll also post in a form you can fill out for your teacher to know that you have showed up here. I'll also post this at the end of the lecture as well, just so we can make sure we get everyone covered. There's an attendance sheet there. Just fill that in with your name and information, and we'll forward that off to your teacher to make sure that they know that you're here. So let's get started here with magnetic forces. So we're going to talk about magnetic forces, which we symbolize by the force sub B, B being a magnetic field, and this force is equal to the charge of a particle times the cross product of the velocity of the particle crossed with the magnetic field of the particle. So what this is basically saying is anytime you have a charged particle that has a velocity and it's moving through a magnetic field, there's going to be a force that's applied on that particle from the magnetic field itself. And this is how we can find the vector of the magnetic, or vector of that force, using the cross product. And I have a few diagrams up there of the right hand rule, where you can take your hand, basically always your right hand. If you have your left hand, you're going to get the wrong answer. And what I do is I put my fingers towards the direction of velocity, where my thumb can equal the force, and I can curl my fingers towards the angle between the velocity and the magnetic field. And you can see that kind of in this diagram here, where here's the magnetic field shooting out this way, the velocity is that way, and they have their fingers, the knuckles are kind of pointing out towards the velocity. You can see you can use your fingers like that as well, kind of, spacing it out, where my pointer finger is pointing in the direction of the velocity, so I point that way. My middle finger points outwards towards the direction of the magnetic field, and then my thumb would point up to the direction of the force that applied on a positively charged. If it's a negatively charged particle that has that velocity flying through, we do the same thing, but then the direction is flipped and you go down instead of up. That's the main difference between them. So that's how to tell the direction. Notice that the force is always going to be orthogonal to the velocity and the magnetic field. So there's always 90-degree angle, because it's in 3 dimensions now, between that magnetic field vector and the force vector. There's always going to be a 90-degree angle between the velocity vector and the force vector. These two angles don't necessarily have to be 90 degrees. They could be any different angle they want to be, but the angle of the force compared to those two angles is always going to be 90 degrees. So the force is always going to stick like up in a 90-degree direction. We'll call it orthogonal in 3 dimensions, like perpendicular to each of them. And you can see here they have the force is positive, going upwards in this direction for a positive charge, and we can say it's going downwards, the opposite of the direction of your thumb, for a negative charge. So using that to find the directions, we can also find kind of the magnitude or the scalar value for the force. And that, I'll make an arrow, force of the magnetic field, the magnitude of that force is going to equal, same idea, Q. We just have VB. We lose the vectors, but then to do that, we need to have this sign of theta, where theta is that angle between them. This angle here between the velocity vector and the magnetic field vector, that's going to equal our theta. Draw that in red so we can really see it. This is our theta here. So we can tell if that angle is 90 degrees, we're going to have the maximum force between them, because sine of 90 is equal to 1. So trigonomic sines, sine and cosine can never be greater than 1. They always kind of oscillate back and forth between 0 and 1, or 1 and negative 1. So in this case, the largest it can be is when sine is equal to 90. The smallest it could be would be is if sine was equal to 0 or 180 degrees. Basically, if your magnetic field is parallel, or say, 180 degrees or 0 degrees from your velocity. So if it's traveling directly into the magnetic field or directly away from the magnetic field, it's going to have a sine, that sine of theta is going to be 0. So your magnetic force is going to equal 0 in that case. We like to denote magnetic fields because now we're talking in 3 dimensions and we're trying to depict this in a 2-dimensional plane. So we have 2 things. I have some of these drawn here below, but if I draw this circle with an X through it, that means it's going into the page. So the magnetic field is coming down into my paper and going through the paper out the back side of it. So it's going into the page. If I draw it, that same circle but with a dot in the middle of it, that's like saying it's going out of the page. So it's a way to depict a a vector in 3 dimensions that kind of extends out of the page itself, where we can have then the other 2 dimensions of our 3-dimensional space being the plane of the paper. We can use this, so if we were to have a particle, we'll call this a positron, which is an electron with a positive charge instead of a negative charge. Same mass as an electron, just has a positive charge to it, and it has a velocity in that green arrow going to the right. So since the x's of the magnetic field, the blue is going to be the magnetic field vector kind of flying down into the page uniformly, I could draw my hand going to the right. Of course, that's the opposite way of my video, but if I draw my hand going to the right, curl my fingers around, it's going to shoot upwards in that regard. So my force is going to be going this way. My magnetic force is going to be going up, because I would go to the right and then I curl my fingers into the page and that would shoot up. So that's a way to determine that force. If it was an electron instead, right, it would go downwards. Just the same idea, but now the force be on an E minus. Okay, is now going downwards, the opposite direction, because we have an opposite charge there. When this happens, the force is always going to be perpendicular to it. So you end up with kind of like this idea of like a centrifugal force, where as long as that charged particle is in the magnetic field, it's constantly going to be having an acceleration of force on it in a perpendicular way. So it'll start to spin and have this kind of radius to it, right? It'll spin in a perfect circle if it's exactly orthogonal to the magnetic field. If it's at a weird angle, then it's actually kind of spiral and create a helix going down. And they use that for like the transition microscopes and stuff like that, or electron microscopes. So they accelerate an electron at a really high pace and it has a wave to it, and then they spin it through a magnetic field and they kind of spiral it down to focus the beam. It's really cool. Anyways, I digress. So we can look at this force. That force of magnetic is equal to the mass times the acceleration, some centrifugal acceleration that we learned in the last term, which is equal to mass times v squared over r being the radius of the circle, some radius. Before we had it kind of tethered to the circle, but as long as that magnetic field is orthogonal to the direction of travel, we are constantly getting this perpendicular force. So that our particle, it will just spin in a circle around like that. So we can use this idea and we can substitute in the value QVB, which is equal to the force magnetic, which would then be equal to mv squared over r. And we can use this to solve for the radius. So depending on what the mass and the velocity of it, the magnitude of the electric field, the charge of it, we could figure out the different radius of things. And we could vary one or two electron or one or two variables, and we could discover, an unknown variable or something to that effect. This is actually how they identified different unknown particles. They would shoot an electron through there, and then they'd apply a magnetic field, and they could see the radius. And based on the radius, they knew they could determine the mass of it, or the velocity of it, or the charge of it, and different things like that. So solving this equation up here for the radius, really just swapping those two across, we can say R is equal to the mass velocity squared over QVB. And notice our velocities are going to cancel out. We're still going to have 1 on the top, but none on the bottom, so that's MV over QB. And if we were to plug in the idea of kinetic energy into that, remember kinetic energy, KE, is equal to MV over MV squared over 2. We can solve for velocity in this case. Solving for velocity, we have 2KE over M square root is equal to our velocity. So using that and plugging it in here, we can say that we have one mass on the top. We're going to have the square root of the mass on the bottom, so we can just cancel out part of that and say it's a square root of mass on the top. So that's 2mke square root over qb. Just substituting this value up here for velocity, we can get this in terms of our kinetic energy. So how much energy is in there as well. Using that similar type of thing, just with our rotational kinematics, we can see that the period, so how fast it goes around per second, would be equal to 2 pi r. It's basically the circumference of the circle that it makes divided by its radius or velocity, how fast it goes around that circle. It tells you how many times per second it goes around. Substituting in velocity into that, we can write that as 2 pi mass divided by qb. We're substituting in for radius, this radius equation that we have up here, putting that into r there, and then simplifying, the velocities cancel out, and we end up with 2 pi mass divided by qb, which is going to equal our period. We denote with t, big capital T. The frequency is going to be the inverse of that, so that's going to say, the inverse of frequency. So 1 over t is the frequency, and then therefore we can find angular frequency, which is just going to equal 2 pi times frequency, which would just be equal to qb over m. So that's kind of the angular frequency of it. So we can use some of these relationships now and solve a few problems. So first we're going to look at a few magnetic fields, and we're going to determine the direction of the magnetic force. So we have a velocity of a particle, we have a magnetic field. So this first one, part A, we have, I'm going to turn a little bit so my right hand's correct. I put my right hand straight down, and I can curl my fingers. In this case, I want to curl out of the page. And when I curl out of the page, my thumb is pointing to, it's pointing to the left there. See if I got that. Yeah. So we know that the force has to be going this direction. It's also important to notice it's a positive charge, because if there's a negative charge, the force would be going in the opposite direction. But this is going to be our magnetic force. Again, my hand's in the direction of the velocity, and then I curl out of the page, coming out of the screen, and my thumb points in the direction of that force. So that's part A. For part B, we have, again, our hand going straight up, but now I need to curl, so I'm going to turn my hand this way. My hand's still going straight up, my thumb is pointing in towards the screen, and I'm going to curl my fingers towards the direction of the magnetic field. My thumb is going to be pointing into the screen. right? So I can say the magnetic force is going into the screen. And one way I remember the difference between into the screen and out of the screen is I picture like an arrow from like a bow and arrow. And if you're looking at the back side of the arrow, so the arrow is pointing away from you, you see the little tail feathers, which is a cross. You know, these little 3, 4 arrow tail feathers coming up. If you're looking at the tip of it, you see this point. So this is the tip coming at you. So it's coming out of the screen. And this is equal to the tail. So it's going down into the paper. That's one way I remember the difference between them. All right, moving on to part C there. Part C has the velocity going to my right, right? And I need to point into the screen. So going to the right, pointing into the screen gives me a force going straight up. So to the right, again, I'm pointing the wrong direction as you. Turn around. So point this way, and then I go into the screen. I'm going straight up. So my force is going to go upwards. I should label force B. So these are it's really just a lot of right-hand rules that we're using and ways to determine that orthogonal cross product by just kind of showing this is the velocity. I need to curl my fingers towards that direction of the magnetic field to see what's happening, what the force is on a positive charge. Here's a few more examples. We've got, so that velocity is going this way, but notice my magnetic field is going the opposite direction. So I mean, I can curl and show it would kind of be in an upward fashion. But if you remember, the magnitude of the force is going to be equal to the charge times the magnitude of the velocity vector times the magnitude of the magnetic field sine of theta. The angle between here is basically 180 degrees, right? Because my magnetic field is going this way, so this angle is 180 degrees, and sine of 180 is 0, equals 0. So this whole thing is going to equal 0. The magnitude of force on that particle is 0 because it's parallel, or in this case like anti-parallel, to the velocity of the particle. So if it's going straight into the magnetic field or straight with the magnetic field, there's no real charge to it. And so this one I can say is just 0 force. And it's kind of, it makes a 0 vector in a weird way. Going on to E, E has the velocity going down into the page, right? So now we're going into the page, and I'm going to curl up. Where's my hand? Going into the page, curling my fingers upwards because that's the direction of the magnetic field, and my force is going to go to the right. Looking at this last one, we're going to go out of the page, and I need to curl my fingers to this way. So I'm going to curl that way, and my thumb's pointing downwards. So again, pointing out of the page, curling my fingers, my thumb points down. So since my thumb's pointing down, this is the force. So that's the general idea behind these guys. Whenever you have the velocity and the magnetic field, we can determine the forces applied to those. But sometimes we know not the magnetic field and the velocity, but the force and the magnetic field, and we need to determine the velocity. So that's what this is asking here. We want to find what is the velocity on a negative charge that experiences the magnetic force as shown. So when I do this, I kind of do the same idea, but instead of starting out with that velocity, I start out with my force, my thumb. In this case, I know the force is going up for part A. The force is going up, right? But to use the right-hand rule, that's for a for a positive charge. This is a negative charge. So I'm going to turn my thumb and point it opposite of the force, right? And then my fingers want to curl towards the direction of the magnetic field, right, which is coming out of the page. So I need to turn my hand all the way around this way and curl that way. So then I can see that the velocity is going to the right. So my velocity would go that way, to the right there. Again, switching the direction of force, so my thumb's pointing down, curling my fingers so they come out of my screen. I have my knuckles pointing that way. So that's the direction of velocity. For part B, again, the force is going up, which means I got to put my thumb down because it's a negative charge, right? And I need to curl my fingers in the direction of that magnetic field. So that leads my knuckles pointing into the screen, right? So that means my velocity is going into the screen that way. There's my V. I guess not, it's just a V of the charged particle. Last one, my force is going this way. My magnetic field is going into the screen. So that means my magnetic field is going into the screen, but my force is going this way. I got to flip it because it's a negative charge, right? So really, I'm curling like this because I did to curl my fingers into the screen and have my thumb pointing this way. So that means my velocity is pointing downwards. I'm not super flexible, so that gets a little hard. But recognize you start out by pointing your thumb the same direction as what it is. Again, this same direction as what it is. And then I need to curl. See, I'm curling away from the screen now. So I need to curl into the screen, so I got to flip my hand upside down. Now I'm curling into the screen, pointing in that same direction. My knuckles are pointing downwards in the direction of the velocity. So that's going to go downwards. Last set of right-hand rule things that I have going on. This is really just they're all good examples of finding those directions. In this case, we have the force and the velocity. We need to determine the magnetic field. And there's a couple things here that we need to determine the direction of the magnetic field that produces a magnetic force on a positive charge. So that makes it easier. We don't have to flip our forces at the beginning. And they're shown in each of these cases. And we're assuming that the magnetic field is perpendicular to V. Okay, so we're going to assume that it's perpendicular. So that means we don't have to worry about any of the sine theta stuff because sine of theta is equal to 1. So in this case, we have a force. I can use it so my hand is kind of flat. I'm going to point it this way. So notice my thumb is the same direction as the force, and my fingers are going in the same direction as the velocity. So the only way for that to work is if I can curl my fingers. In this case, I'm curling it out of the page. Of course, when I look at it, it's backwards. Now I'm curling that way. Velocity is that way. That's going out of the page. When I look at my screen, it's going into the page because mine is all backwards from that. My camera is mirrored. I gotta fix that next time. So yeah, if you do this on yours, point your thumb in the direction of velocity, point your fingers, the thumb in the direction of the force and the fingers in the direction of the velocity, and then curl your fingers. With your right hand, you should be curling it down into the page. So your magnetic field should be going into the page there. Similarly, with this one, if I point my fingers down and my thumb pointing out, I would curl this way. Oh, sorry. The force is going into the page, so I have to go this way. Force is going into the page, and I would curl that way. And again, my camera's mirrored, so I'm really be going to the left-hand side. The last one, putting my thumb in the direction of force, my hand in the direction of velocity. Again, camera's mirrored. When I curl my thumb, I'm coming out of the page. So this is the magnetic field for each of these and the vector, the direction of those magnetic fields, using the right-hand rule to kind of solve for those equations. So depending on which value you have, if you have the force and the velocity, you can determine the direction of the magnetic field. If you have the magnetic field and the force, you can determine the direction of velocity. And if you have the magnetic field and the velocity, you can determine that direction of the force. We can apply these equations we have, to problems to find the force on different charged particles that are flying through magnetic fields. In this case, we have a cosmic ray proton, which is moving towards Earth at 5.3 times 10 to the 7 meters per second. That's really fast. It experiences a magnetic force of 1.64 times 10 to the negative 16 newtons. They want to know the strength of the magnetic field if there's a 44-degree angle between the magnetic field and the proton's velocity. So let's draw that out for a second. So if I had some velocity, and it's going to be coming down like this. This is my proton. And let's say Earth's magnetic field at this point is 44 degrees. So I'm going to draw that in this light blue color. So it's going kind of, I want to draw it so it's kind of this way. We can draw it like this. And we know this is 44 degrees. I don't know if I actually drew it 44 degrees. I don't think I did. Pretty sure I didn't. Maybe that's better. Calculator. Anyway, we have that type of situation where the magnetic field and the velocity vector have a difference in 44 degrees between them, and we know the magnitude of force that's given on it is this guy, 1.64. So I can say the magnitude of force B is equal to 1.64 times 10 to the negative 16 newtons. And the velocity is equal to the magnitude of that velocity, 5.3 times 10 to the 7th meters per second. And so we need to determine what is the magnitude of the magnetic field. There it is. The strength of it, they call it, which is basically the magnetic field. We can determine that magnitude of it using the equation that we had for the force. So if I said that force is equal to, it was Q first, V B sine of theta. That was the equation we had. We know that the charge of a proton, Q, is going to equal 1.6 times 10 to the negative 19 coulombs, and sine of 44 degrees is the last thing we need. So we can plug everything in here now, where first we should solve for the magnetic field. That's what we're really looking for. So rearranging this equation, I can say the magnetic field is equal to the force divided by QV sine of theta. Plugging in values for that now, we get 1.64 times 10 to the negative 16 newtons. That's the force. We're going to divide that by 1.6 times 10 to the negative 19 coulomb. And we're going to also divide by the velocity, 5.3 times 10 to the 7th meters per second. Multiplying at the bottom by sine of 44 degrees. And let's plug this into our calculator. So we have 1.64 times 10 to the negative 16 newtons divided by 1.6 times 10 to the negative 19 coulombs times 5.3 times 10 to the 7 meters per second times sine 44. And I hope I'm in degrees. 0.0, say 2.78 times 10 to the negative 5th Tesla. Tesla is the units of a magnetic field. So I'll just say it's 2.78 times 10 to the negative 5 Tesla. And Earth's magnetic field is of the order of 10 to the negative 5 Tesla. So our answer makes sense. That's the idea. So that's how we can use that equation, this guy here, to solve for the magnetic field. If we have the force and the angle between the different velocity and magnetic field vectors. We're going to look at another one now. This one's a mass spectrometer. Mass spectrometers are a lot of fun. They are able to split atoms up and then separate them by mass. And they use a magnetic field and velocity of charged particles. If you ever threw something in there and it split it up, and the uncharged portions you can't actually detect. It's only the charged ones, because the uncharged ones don't spin in the magnetic field like this. This is a little diagram of it. We basically have a ion source. So there's something that's creating these ions. Usually there's a compound and they're putting radiation on it to break the compound bonds, and they break at specific areas. And then they fire it through here to that little slit. Here they have a electric potential to give you an electric force going up to counteract the magnetic force going down. So those particles fly fairly straight. Once they get through the slit, the electric potential is gone, so now they spin, and they spin around in that circle. And based on the mass of them, they spin at different radiuses, because the acceleration on them would be the same, but since the mass is different, the radius that they curve is different. So we can determine what the particle is, what the mass of that atom is, based off of the radius that they have. And here we're going to calculate the difference of the radiuses between two different oxygen isotopes. So the mass spectrometer, which is being used to separate common oxygen-16 from the much rarer oxygen-18. We taken from a sample of old glacial ice. And they do this so they can see the abundance of oxygen isotopes in, the old atmosphere. So they take glacial ice, which was frozen thousands and thousands of years ago, and they can determine what the composition of the air was when it was frozen. They tell us the ratio of these masses of the two isotopes is 16 to 18. And the mass of oxygen is 16 is 2.66 times 10 to the negative 126. I think that should have just been 26. Let's change that. 26. That's hard to read. I'll write it down here. So I'll say mass 16 is equal to 2.66 times 10 to the negative 26 kilograms. There it is. And they're slightly charged. They have to be charged to actually curl during that magnetic field. And they travel at 5.4 times 10 to the 6 meters per second. So their velocity is equal to 5.4 times 10 to the 6 meters per second. And the magnetic field that they're traveling through, which based on the diagram is coming out of the page, that B is equal to 1.1 Tesla. They want to know what is the separation, and they give us this delta D, they called it. Delta D, which is equal to 2R1, or R2 minus 2R1. Notice R2 is longer than R1, so they just want this little distance in between there. What is the difference in the radius? When they actually hit their targets, what's the difference in their distance between them? And it says, what is the separation between their paths as they hit their target after traversing a semicircle? There's that semicircle. And they use that semicircle so they can actually use the radius, twice the radius, to determine that delta D. So we can use some of the equations that we've learned. Earlier we defined the radius r is equal to mv over qb. So using that, we can say that delta D is going to equal 2 times, say, the mass of the oxygen 18 isotope times the velocity divided by qb minus the mass of 16 isotope, so the oxygen 16 isotope mass, times the velocity divided by qb. So that's really, it's giving us the difference in the radius. And we have to do 2 because we're looking at the diameter. We're looking at this whole distance here. Now, the ratio they give us between the two isotopes is 16 to 18, where the mass of oxygen 16 is, well, this guy here. So since we know oxygen 16, let's write oxygen 18 in terms of oxygen 16. So we can say that the ratio M18, or say M18 to M16 is equal to 18 over 16, which means that M18 is equal to 18 over 16 times mass of 16. And that way we can substitute this mass times the mass ratio N for mass of 18, or the oxygen 18 isotope. Only a few more variables we have to define here. The Q is going to be equal to 1.6 times 10 to the negative 19 coulombs. And I think we have everything else there. We have the magnetic field, we have the velocity, and the mass of 16. So now we can calculate what this distance is. I'm going to factor out a few things. Let's write it again below. So delta D is equal to, factoring out the common terms, the velocity is common, the charge is going to be common, the magnetic field is common between all of those. So factoring all of that out, I can say that's 2 times V divided by QB. I can even factor out the mass 16, because I can really, since I have this right here, let's just write it in first. So mass 18 minus mass 16. But this is going to be equal to 2V over QB times, factoring or substituting in this value to there. We have 18 over 16 times mass 16 minus mass 16. So I can then factor out that mass 16. And we get 2V over, that's Q, QB, mass 16 times, say, 18 over 16 minus 1. And now we can plug in our values. So I'm running out of space. I'm going to make some of this a little bit smaller. Plugging in the values, we have delta D is equal to 2 times 5.4 times 10 to the 6 meters per second times the mass 16, which was 2.66 times 10 to the negative 26 kilograms. We're going to divide that whole thing by 1.6 times 10 to the negative 19 coulombs. And see, zoom in so we can see that better. I know I'm right on the edge. And we're going to multiply that by, or divide again, by the magnetic field, which is 1.1 Tesla. And we're going to multiply that whole value by this ratio, 18 over 16 minus 1. If I substitute in 16 over 16 for 1, giving me common denominators, I can say that's going to be 18 minus 16 all over 16. The difference between 18 and 16 is 2. So that's going to equal 2 over 16. Or really, that simplifies to 1 over 8. So we can then plug that into our calculator, see what we get. So that's 2 times, I had 5.4 times 10 to the 6 meters per second. I'm going to multiply again by the mass of isotope 16, which is 2.66, times 10 to the negative 26 in kilograms. We're going to divide everything by 1.6 times 10 to the negative 19 coulombs. And we're going to multiply by 1.1 Teslas. And then we're going to multiply all of that times 1 over 8. So again, that's 18 minus 16, which is 2, divided by 16, which simplifies to 1 over 8. And we get 0.204 meters. Which is equal to 0.204 meters. Or about. So that's the distance that the two isotopes end up at this target location on the diagram when they're shot through that magnetic field. 1.1 Tesla is a pretty strong magnetic field. Remember previously we said Earth's magnetic field, which is what drives all the compasses on the planet, is only 10 to the power of 5 Tesla, or power of negative 5 Tesla. So we're at 1.1 Tesla. So it takes a lot of energy to create that big of a magnetic field. Let's move on. We're going to talk about magnetic fields generated by a long wire. So when we have current flowing through a wire, I'm going to draw a wire here. If there's current flowing through that wire, it's going to create this magnetic field radiating out around it. And we could determine the direction it circles around using this other version of the right hand rule, where you take your right hand and you basically, assuming this pencil is my wire, I can grip it and I put my thumb in the direction of the current. When I do that, my fingers represent the direction of that magnetic field radiating out from it, and depending on the distance, it'll continue radiating out over it. It gets weaker and weaker and weaker the farther you get from it. So I can define this distance if I wrapped my hand around this. Again, I'm going the other way. If you wrap your hand around this wire that I've drawn, we can define that distance as going kind of in this direction. There. We can calculate the magnitude of the magnetic field as well using this equation where B is equal to mu naught, which is the permittivity of free space for magnetism, times the current divided by 2 pi r, where r is the distance away from the surface of the wire, or the center of the wire. Usually the wires are pretty thin, but we have the distance away from it. So if you get 10 centimeters away, you'd put 10 centimeters in from there, and that would be the same magnetic field all the way around that wire in a radial fashion. We can also determine the force that this magnetic field would generate on another length of wire next to it. So I'll say the force of 1 on 2. So wire 1 on wire 2 would equal the current in wire 2 times the length of wire 2, which is a vector, and it's going to be a cross product with that magnetic field from 1. and we can find the scalar value. This is going to be a vector. So the magnitude F12 is going to equal then I2 L2 B1 sine of theta. Just like we were doing before, but now instead of a charge, we have a current and we have a length. So we can also look at this as in a force per length. And notice, before I move on, that if the wires are parallel, sine of theta is equal to 1. Because theta is equal to 90 degrees. Theta in this case is kind of the angle between the magnetic field and the current. And since the current, I guess in this case it's not the magnetic field, I'm sorry, the magnetic field and the length of wire. So the magnetic field is coming out from the first wire, and if the second wire is parallel to that, it's going to be completely perpendicular. The angle between those will be 90 degrees, and therefore sine of theta will be 1. So on two parallel wires, we could then write that force 1 to 2 is equal to I2 L2 B1, where B1 is wire 1 is generating the magnetic field, and wire 2 is having that feeling the force of that magnetic field. So that's why it's the force of 1 on 2 when I write 1 2. And we can look at it as force per length. And in this case, we just take that same equation, 1 to 2, we divide by L2. By dividing by L2, this is equal to I to B1. And then we can substitute in this value here. In this case, since it's B1, it's going to be I1 that we have up there. So substituting that in, we're going to have the force of 1 on 2 divided by the length of 2 is going to equal I2. Now we're putting in mu naught I1. So I'll just put mu naught I1 divided by 2 pi. And now our R is really the distance between the two wires. So I'm going to say R of 1 to 2. That distance between the wires, 1 to 2 in that case. And this is an equation that we're going to use often to see that the force that one electric wire has on other electric wires that are next to it. We're going to do a problem with that right here. So in this figure shown below, it shows a long wire, long straight wire. That's this top one up here. And that wire is near a rectangular current loop, which means this loop down here just has a current kind of going around it and around it. And we're going to say it's a constant current at this point, assuming there's basically no resistance in that wire. We want to know what is the direction and magnitude of the total force on the loop. So, like we were saying, there's going to be this magnetic field that radiates around this long wire. And we can put our hand on it, put our thumb in the direction. In this case, my thumb's going this way. But we put our thumb in the direction of it, and we can see that this wire is going to be going down and then under that wire. It's going to be shooting down this way. It's going to be kind of radiating outwards around that. And eventually it's going to hit this wire and cause a force to happen. And it'll happen at every point kind of along that wire. That's why we're looking at the force per length. Right? And the force per length. So the force of, I'm going to call this one 1, this one 2. Force of 1 on 2 by length 2. Well, the length of this is just 30 centimeters at the bottom. But we can use that same equation we defined here. I2 mu naught I1 divided by 2 pi R 1 to 2. So I'm going to write it as just mu naught in the front, I1, I2, just to keep it nice and orderly. And that was 2 pi R1, 2, the distance kind of between them. And for every segment of this wire, it's going to feel a slightly different force, right? Because the distance here is 7.5 centimeters. But the distance to this back wire here is going to be an additional 10 centimeters. So it'll be 17.5 centimeters. And then looking at these two segments here and here, well, those two are going to basically cancel each other out. For one, the direction of this wire and this wire doesn't change. But for every point along this wire, with the current going this way, we have an equal point going this way, the current going that way. So we still have our charged particles, but they're going to be going in the same direction as the magnetic field, so you're not going to see much force on them at all, and even if they did, they would cancel each other out because the directions of the currents are going the opposite direction. Moving on, we could plug in our values now for this. Listing those values, we can say that L2 is equal to 30 centimeters. I'm going to write that in meters. That's 0.030 meters. We can see that we don't know the force. That's what we're looking for. Mu naught is going to be equal to 4 pi times 10 to the negative 7 Tesla meters per amp. That's going to be a standard value for the entire universe in a vacuum, is mu naught. It's the permittivity of magnetism in free space. The current I1 is going to equal 15 amps. It's listed there. The current 2 is going to be equal to 30 amps, listed here. Okay. You can say R1, or say, I guess this is 2, so this is 3. And say R1, 3, or say 1, 2 is equal to 0.0075. No, too many zeros. 0.75 meters. And then R1 to 3 is going to be equal to 0.175 meters. So that's just the distance here and the distance all the way down. Draw it there. And we want to know the net force of these. So we can find the force of each of these wires, this segment and this segment independently, but we want to know the net force on them. And since one of them is going in one direction and the other one's going in the other direction, one of those forces is going to be negative and the other one's going to be positive. In this case, we're going to define this one as being a positive force and this one being a negative force. So we can say that the net force is equal to the force of 1 on 2 minus the force of 1 on 3. Now writing that out using our equations there, we can solve for these problems. So the force is going to equal mu naught times 15 amps. Well, let's say mu naught I1 I1 I2 divided by 2 pi R1 to 2 minus mu naught I1 I2 divided by 2 pi R1 to 3. And we can factor out all the common factors we have from there. So the common factors I can see is mu naught, because that's in both of them, I1, I2, divided by 2 pi, and we can multiply that by then the difference between R1, 1 over R1 over, 1 divided by R1 to 2, minus 1 over R1 to 3. Plugging in values for these now. Make sure I can see my values. I can say mu naught is equal to 4 pi times 10 to the negative 7 Tesla meters over per amp. Current 1 was 15 amps. Current 2 is 30 amps. I'm going to divide that all by 2 pi. I'm going to multiply this by 1 over, let me say 0.017 or 0.075 meters minus 1 over 0.175 meters. All right, plugging that into our calculator. We get 4 pi times 10 to the negative 7 units of Tesla meters per amps, big capital A, times 15 amps times 30 amps divided by 2 pi, multiply that whole thing times 1 . I wrote this wrong. That's what's throwing me off. This needs to be this should be 1 over R12 minus R13. So this, just draw that line straight and subtract that. When I factored everything out, I factored that wrong. One over, unless I did it right, minus 0.175. Maybe I did it right the first time. Same thing. Put it back how I had it before. Oh, undo. 0.175 meters. Am I missing something? I forgot to divide by the length. That's what it was. Whoopsie. So I need to multiply by the length here times 0.03. 0.03 or 0.3 meters. That's better. Gives us 2.06 times 10 to the negative 4 Newton. So that's negative 4 would be 0.000206. So let me fix this. I forgot to put in my length there. I should multiply that over to find that force. So I need to input length of 2 in there, length of 2 in there, length of 2 in there, which, and then fix that. Sorry about that. Okay, adding in 0.3 meters there, which is my length. This is equal to 0.0000206 newtons, or 2.06 times 10 to the negative 4 newtons. So that's the net force on this wire. Notice that this first part here has a greater force on it because it's closer to the wire generating the magnetic field, where that farther one has a weaker force. Even though the same current and the same length are there, the force on the farther wire is going to be less. So the net force is going to be greater than 0. That's all we have for today. Thank you for watching. Again, I'm going to paste form to the attendance sheet if I can find it. Definitely fill that out and get some extra credit. And I'll see you tomorrow. Enjoy the semi-nice weather we have. It's not snowing, raining, or icy, so that's always a good thing.